So, boys and girls, which one do you think so? If I draw another one next to it, this side should point to south, and obviously this side should point to away from north. Yeah. So actually these two are fine. The orange one is correct. While this one should also point to south. This one point to south, and this one kind of point to south. And while this one, left or right? Left or right? I mean your direction, to your left or to your right? To your right side, because it wants to go to south, right? And also you can see the pattern as well. They should follow the same direction. And this one also.
So we draw because it's only.
I think that may be better.
Just point to the tip of
this.
So we just point to the tip.
If we got more compass, then it should be very perfect that it gives you the shape of the magnetic field. So you can try to change it. Correct your answers into this. Are you okay with that? The black one. The black one is the answer. First are you okay with that? Yeah? You may want to correct that. Now I need to ask you then. How come? I'm not sure if you find out something very suspicious. How come the compass, normally when we use it on the Earth, it points to North Pole or South Pole? North Pole, right? With the direction we define. How come now it's pointing to South then? Sorry? I don't want to say something.
It's the magnetic field.
Yeah. Very good. The idea of saying North Pole geographically is different from the magnetically, the North Pole. So if you imagine this is the Earth, and we try to open it, we can't actually see a magnet. But it will act like a magnet. It will act like a magnet with this is what pole? This is the South Pole. Remember, your compass points to the South Pole of the magnet. So this should also be South Pole if you keep everything the same. This will be North Pole. So actually the you mean this arrow? Oh, these are gravitational field. Yeah, those are something else. Maybe I shouldn't confuse you. Yeah, that was talking about the gravity. It's all pointing towards it. Alright, so this is how the compass actually works. And maybe I should ask you a question. If you read books, many books about like science, you may know. How come the Earth will have magnetic field inside? Like moon, probably not. I don't know too actually. How come the Earth would somehow, not because of gravity? Sorry? Compass what? The composition of the Earth. Close. Something to do with what's inside the Earth. The core, what does it have?
Metal.
Iron. Metal. Close metal. More importantly, uranium. Not a lot. Nickel. Iron. Maybe I should ask you a question first. You know iron, cobalt, nickel, these are the material element you learned from chemistry. They are magnetic, right? If you put a compass next to it, do you think they will point to that material or away from that material? Say again? Heidi? It won't move at all. Actually, it has no effect. Do you know that? Do you know that? If not, I can show you very quickly. Yeah, we have got a whiteboard. This is a magnet, of course. This is a sorry. You can see, right? I guess you can see this is also magnetic. That means it can be attracted by the magnet. Okay, it can be attracted. Both directions though. If I put the compass here, Natalie, can you help me to see? Is there any changes? Is there any changes?
No.
Not really. Not really any changes. So this doesn't affect anything. This can experience the magnet. Same as the whiteboard. The whiteboard can experience the magnet. But in itself, they don't give you the magnetic force. What I want to say is, maybe I'll give you some hint. Later on, we will, in the next lesson, we will try to build an electromagnet. Anyone heard about electromagnet?
The circuit.
Very good. You learned in the previous chapter that about the circuit breaker. Primarily, how does it work?
If there's a circuit passing through it.
If you have a circuit, more precisely, if you have what? Current. Very good. If you have current, I, passing through a circuit, passing through some wires, and what will you have?
Magnet.
You have the magnetism. Alright, you have the magnetic force produced. And we are going to do that so that you will see, because I don't think you have made one before. This is a hint. How does the Earth will be a magnet? Sorry, say again? It rotates. It rotates. How come the Earth will have magnetic field by its nature? Think about, just now I mentioned electromagnet, and also it's something to do with what's inside the Earth. The course. Putting on energy. Do you know what's inside the Earth?
Fire.
Say again. And what's so special about that? Very good. Inside the core, of course we didn't actually cut the Earth into half and see it, but we know inside there are some substances that are charged. They are actually charged because they are very high temperature. I'm not sure if you have heard about that. High temperature, and if you melt something in high temperature, that would be plasma. And plasma is something that carrying the charge. And if they are flowing, there's a convection. There's a convection inside the Earth core, just like the current. Just like the currents with the circuits, and they will have the magnetic field. And that's why we have the magnetic field inside the Earth. Are you okay with that? So far? Okay? I find a very interesting video that I would like to show you how magnet is made. Anyone know how magnet is made actually? Like this one. Trust me, it's not someone go to mine and just find out something, hey, this is magnetic. They don't do that, right? It's artificially made actually. How do we make it? Induction. Pulse. With what? With another magnet. So where does the first magnet come from? Electricity. Something to do with electricity. That's true. That's the electromagnet. I'm asking you this one. This is called the permanent or temporary magnet? Definitely permanent, right? Because no matter where you carry it, it's still magnetic. Let me show you the video.
Do you play RPGs?
See your field of force causing this globe to levitate, but it's not magic, it's magnetic. An essential part of our daily lives, magnets are used for a lot more than just sticking stuff to the fridge. They help run motors and generators, and are also found in computers, televisions, and microphones. Magnets occur in nature, but only 2 centuries ago, scientists figured out how to make them using metal and electricity. Production at the magnet foundry begins with the creation of a mold. A tray containing 4 magnet shapes is loaded into a machine that fills it with sand. A worker removes the pattern and smooths the surface dimpled by the machine's lid. Then it's back inside. This time, the machine pumps in gases that chemically alter the sand, hardening it in a matter of seconds. The sand slab is now a durable mold. And these molds are made in a wide variety of shapes and sizes.
You don't mold, right? Just like making cakes or some other things.
Now it's time to mix together the ingredients for the magnets themselves. They include copper, cobalt, sulfur, nickel, pure iron, aluminum, and titanium. All of these metals are loaded into an electrical induction furnace.
What material again?
Nickel,
Iron, sulfur, titanium, copper. Okay, okay, very good, very good. Are these all magnetic?
No. Not all.
Not all. Very good. Is copper magnetic?
No.
Copper?
No.
No, copper is not. Alright? And sulfur?
No.
It's not as well. So you can see it's not completely using magnetic elements. Can you see why?
It generates a pulsating electromagnetic field that heats the metal to almost 3,000 degrees Fahrenheit, melting everything into a molten soup. The metal gets poured into the molds. Because the gases that harden the sand are highly flammable, the molds burst into flames. Still ablaze, they slide to another part of the foundry where workers knock them to the floor and bust them open with sledgehammers. This lets the air, cooling the molds and allowing the gases to burn off.
The mold will be destroyed because it's sand. It's okay to be destroyed.
Do they reuse it?
So that they can. Sorry. No, they will make a new one. So whenever you make a magnet, you make this mold. It's something industrial method that is not too relevant to physics. More like 2DT instead. Otherwise, you can't get it out.
All of the pieces are shoveled into a bin, and workers separate the metal from the sand chunks using what else? A magnet. But these metal pieces aren't yet magnetized themselves. That will come later. A set of rings designed for use in electric motors is threaded onto a copper pipe. The ring-covered pipe is placed in a tube. Then, silica sand is packed in to hold the rings in position. Both ends of the tube are sealed with concrete. Then, it's into an electrical furnace. It heats the tube until it's red hot. This superheating primes the rings inside to accept an electromagnetic field, which will be delivered by this metal rod. The rod slides down the center of the copper pipe and is clamped into place. Water keeps the pipe from melting as a low-voltage, high-current charge is delivered to the rings inside. Workers break open the seal.
How much voltage is it? This is actually current. But you can see how much current.
6,000.
6,000 is a lot of. It has to be high voltage as well in order to get this high current. Alright, you can see 1,000 times 1,000 here, so it's high, very high.
Workers break open the seal. The process has left the rings mildly magnetized. Any rough edges are smoothed away. At this point, the magnets are pretty useless. But this machine empowers them with a strong electromagnetic charge. The establishment of that weak magnetic field earlier ensures that the magnetization is now properly oriented. Now that's some serious magnetic muscle.
So most important is what? The last part where you need to have a high current, right? You may wonder, so how come a high current or high voltage can change that? There is another video, but I don't think we should show it today because we don't have time. But you can think about like that. It's something to do with more advanced physics. But you can imagine, can you help me switch on the light? That inside the magnet there are different parts, different small parts, different domain, we can say. And each of them have different direction, normally. Like very random for a material that is not magnetized. But what you do when you pass a very strong current or voltage to it is you are going to align them in the same direction. So all this may be, let's say, all point to the right now. And that can create a very uniform magnetic field that you will have.
How would electricity uniform?
That's we find out simply. Like later on, electricity and magnetism are very closely related. Okay, but it's okay if you don't understand that so far right now.
What happens at the end when he places like the magnet on the piece
Yeah.
of metal?
The current pass through.
So pass the
Yeah, the magnet. Yeah, that cable is more like a part of the circuit that.
No, but I thought like before he
pass through the
I think after it cool down, you have to do it again. That should make it more durable, I guess. So right now, just two very simple questions. Right here, if you use some soft ferromagnetic, that means you can change easily. Ferromagnetic means you can change easily. To create certain magnet. What magnet do you call that? Temporary. Yeah? I think you can just check it yourself. Temporary. While the lower one, if you use half ferromagnetic, just like what we have now, it will become a permanent magnet.
So the magnetism will fade away.
For temporary, yes, it will fade away. That's why soft ferromagnetic like what material? They can change easily. Iron, very good. Iron, cobalt, what are the other two? Cobalt and nickel. Again, these three are soft ferromagnetic. That means if people just now they use these three only, or pure iron to make magnets, it will be quite stupid because at the end of the day, after maybe a few days, the magnet is gone. It's not magnetized again. So they have to do it again. The reason why they mix with copper or sulfur or some other element is those are hard ferromagnetic. In your daily life, you may not find copper is magnetic. If you put a magnet to copper wire or copper water pipe, you don't find them magnetic. But if you only apply a high current to it, they will become magnetic and they will just stay there because it's hard for you to change it. Do you see the point of hard to change? Doesn't mean it cannot change. And also the fact that once you change it, you can't change back. So copper, things like copper, you can change them with high voltage and it's quite permanent. Although we can't say forever, but quite permanent compared with iron, cobalt and nickel. Are you okay with that? Okay. Anna, help me to get a new part.